We all needed a break from the election. Okay, so welcome. You know, hopefully people have gotten some sleep. So thanks for turning your homework in. I think I got everyone's homework. I am assigning the last and final problem set today. So I was deciding whether to assign it today or next week. I'm going to assign it today because it is kind of long, so I want to give you more time. So, how am I? Can you check that camera? Is that good? Okay, perfect. So the announcement is your last problem set is posted. I'm not counting your Monte Carlo project as a problem set because that's a project. So this is problem set 7. Is posted to Canvas. This will be your last problem set. I'm giving you a week and a half for this because it's kind of long and it's not an easy problem set. So I'm giving you more time. Spend some time on it. So I'm making it due Tuesday, November 17th. So it's gonna be due Tuesday, November 17th. So basically what the rest of the semester looks like then, right, is this is a week and a half. That's your last problem set. And your final exam is a week later. So you have a week when this is due to just focus on the final without any problem sets. And then after your final, your Monte Carlo project is due December 10th. So you have quite some time for that. And probably what we'll do is we'll plan some office hours / help sessions for after the final for the project. And so that way you can really focus on this and the final. You can focus on one thing at a time for this class, right? No guarantee about your other class. So this is the last problem set. Like I said, it's 5 problems. It's a little challenging. If you think about what we've been doing in class, we've been doing phonons. There's not many homework problems I can actually ask you about phonons. Right, so there's only one problem on phonon, so it's kind of light on the phonon material. Then your second problem is going to be an Ising model type problem. You're going to solve the non-interacting spin system, okay, which you actually can do. So that's the second problem. The third problem is going to be something we haven't done in class at all. You're going to derive what's called the Fermi-Dirac distribution. So that's a really important distribution in stat mech. It's a first step if you're going to treat the electrons in a metal, right? So to treat the solid completely, if you have say copper or something, you have to do the phonons, which we did. Then you have to do the electrons. We just didn't have time to do that. The first step is deriving the Fermi-Dirac distribution. So I kind of walked you through that problem in the homework. So that's a fundamental distribution that I wanted you guys to see. And then you have 2 more, so there's 5 problems total. Problem 3 and 4 are more practice working with this classical partition function, right? So I gave you proved on your last problem set that this classical partition function was reasonable, right? You proved you got the ideal gas result. And I'm going to give you 2 more problems working with it. You're going to derive equipartition, and you're going to derive the Maxwell-Boltzmann distribution. And I know we didn't do this in class, but that's part of the homework is to supplement with important concepts that we haven't done in class. So now you have 3 problems practicing the classical partition function. And so we'll have 2 office hours for this homework, which is nice, right? So I'll have office hours next week, you can ask questions, and the office hours the week after. So you have 2 office hours for questions, okay? That sound good to everyone? I like when I say, does that sound good? Everyone nods, right? That's great. It's kind of like a rhetorical question. Okay.
That sounds bad to me, actually.
Okay, well, we'll just, no problem set then. Okay, I know what I was going to do before I get started. I was going to do a little aside review on Euler's formula. Everyone comfortable with Euler's formulas and hyperbolic sines, cosines? We're going to review them because we're going to use them today, and I just want formulas down. Let me just do it right here. So before we get started, let's review Euler's formulas. and I'm writing to the side because it's kind of a side. You don't have to copy this down. If you have these all memorized, don't worry about it, right? And really we're going to use the hyperbolic cosine and hyperbolic sine today. And the way you remember that is through Euler's formulas, right? So what Euler's formula is you can write cosines and sines as complex exponentials, right? And so Euler's formula is that cosine of x, right, is e to the ix plus e to the minus ix over 2. How do you prove Euler's formula? You don't know?
It's the Taylor expansion for e dx.
Right, so to prove it, you would Taylor expand. So you Taylor expand to the left and you Taylor expand to the right, and you prove they're equal. What happens here, right? The cosine is an even function. When you Taylor expand an exponential, you get even, odd, even, odd, even, odd powers. Because you have a plus sign, the odd powers cancel. So you know you need a plus here because you know that you need the odd powers to cancel so you get an even function. Does that make sense? So that's how you remember the signs there. The sine of x then is an odd function, so the even powers have to cancel. Right? So you have e to the ix, now you need a minus sign, so the even powers cancel. And then you need to divide by 2i to get rid of the imaginary number and the odd powers. Okay? So that's kind of how you remember Euler's formulas. And so Euler's formulas give you a nice way to remember what the hyperbolic cosine and hyperbolic sine are. So the hyperbolic cosine is you just take Euler's formula for cosine, you throw away the imaginary i's. Right? So this is just e to the x plus e to the minus x over 2. Just the same as this, except you've thrown away the i's, and hyperbolic sine is e to the x minus e to the minus x over 2. Okay? So, what I like to do when I'm remembering these, I like to write these down first, and then I just use the analogy to remember these. Okay, so those are Euler's formula, and people say, oh, I don't know what hyperbolic cosine and hyperbolic sine really mean. Well, you can, if you don't remember what these look like, just interpret them in terms of exponentials. You know what I mean? So you can always fall back on these exponentials if you need to sketch the functions, right? Even if you don't really remember what these functions look like. Okay, questions on that? Everyone kind of have seen that before, but maybe it's a good refresher. Okay, so we're going to use those today. So, what are we doing today? Can someone check me over here? Is this good?
Yep.
Okay, great. We are plugging along with the Ising model. And what we're going to do today is we're going to solve the 1D Ising model, hopefully. We have time. So let me draw my diagram on the board. We did this last time. I'm going to draw a smaller lattice so I don't waste a bunch of time drawing spins, right? Last time I drew a big lattice. Okay. That's really uneven, but you get the point. Okay, we have spins in the lattice, up, down, up, down. Okay, you fill your lattice with spins. We may have a magnetic field H. Okay, and we're going to characterize we have n spins. Okay, and we're going to label each spin I, right? And we're going to say each spin is characterized by SI can be equal to plus or minus 1, right, for each spin. And spin has magnetization. The essentially direction of the spin times the magnetic moment. So MI equals mu SI is the magnetization, where this quantity mu is the magnetic moment of the spin. Right? And so if you wanted your Ising model to have physical interpretation, this could be a spin, this could be a system of protons or something. Nuclear spin, you look up the magnetic moment of a nuclear spin, and you put that in. If it's a system of electrons, you look up the magnetic moment of an electron and you put that in. Okay. What we said is that different Ising models come from different approximations of how these spins interact, right? And so what we're going to do is we're going to choose a model for how the spins interact. For how spins interact, okay? And model 1, we wrote down last time, is that they're non-interacting, okay? Non-interacting. What I mean is that they're not interacting with each other. They're only interacting with the field. And then what we said is that energy of the spin state, okay? Remember last time we said the state, let me just write that down. State of system is specified by all values of these SI, right? So we can write the set of SI. We need to specify this set, all these spin values to specify the state of the system, which is just a vector, which is just the value of S1, S2, Sn. Okay? So this is the state, that's how we specify the state of the system. This is, the analogy, analog to a quantum state, right? So my energy function depends on the state of the system, which is the set of spins, and if it's non-interacting, it's just minus, I have to sum over all the spins, H, the value of the field, times the magnetization, which is mu SI. Okay? And so that's my non-interacting system, and this is going to be problem 2 in your new homework. Okay? So this is problem set 4, problem set 7, problem 2. You will solve the partition function for this. You think anyone can do that right now? Do you guys have an idea how you would do that? Think about it. It's a non-interacting system, right? We know non-interacting systems, the total partition function factors into a product of partition function for each particle. In this case, it will factor into a product of partition functions for each spin. Okay? So that's how you solve that problem. So that you're doing your homework. But unfortunately, that doesn't really, that doesn't give us a phase transition. We'll talk about it later. And so we have to go to a more complicated model. So our second model is, this is basically the most common Ising model, where you have interactions between nearest neighbors. Okay? So you let the spin system have interactions between the nearest neighbors on the lattice. And this is basically the only interaction model we're going to talk about. And so I'll say this is the most common Ising model. So if someone says the Ising model and they don't specify what the interactions between the spins are, they're probably using this model. Okay, so this is the default model, unless you're specifying something more complicated. So let me just write it down, and then I'll explain it. So in this model, we have an energy function which looks like this. E of SI, okay? We still have this term, because my spins still interact with the field. Well, I have that term if I have a field. If I don't have a field, I can just drop it. So sum of I equals 1 to n h mu SI. So that's the interactions with the field. But now we have another term, and I'm going to write it down, and I'll explain it. So we have the other term looks like minus J. J is what you call a coupling constant. And now we have a double sum. I'm going to write this I comma J with a prime. It's a restricted sum, SI, SJ. Okay? So that is the energy function for my interacting system. And this prime indicates that it's a sum over neighbors. Okay, so sum includes nearest neighbors. Okay, so what it means is this. What I have to do to evaluate this term is that I have to pick a value for I. Maybe I is this spin right here. Okay? So I is that spin. And what I have to do is I have to include a sum over this spin and its nearest neighbors. In this case, I have 4 nearest neighbors. This one, this one, this one, this one. Okay, so my terms here would be this pair of spins, this pair of spins, this pair of spins, this pair of spins. Okay, so these neighbors enter, right? So these are the interactions that you have to sum up in that sum. Does that make sense?
What happens to something on the edge then?
That's a great question. Let's talk about that later.
Okay.
We're going to use periodic boundary conditions. We'll talk about it with 1D, and we'll talk about it with 2D when we do the project. But assume you don't have to worry about the edge. Does that make sense? Okay, and you're not going to double count. So, you know, you count this interaction with this once, right? You don't count this, and this. Okay. So if you sum over this spin and you include this interaction, this interaction, this interaction, this interaction, then when you go to this spin, you only include this interaction, this interaction, and this interaction because you've already included this one, right?
Is that restriction goes by than just the asterisks? Is it implied that every interaction is counted once, or do we need to divide them out?
Yeah, no, that's implied. That's a good question. So this the prime indicates a restricted spin where you're counting once every interaction between neighbors.
Okay.
And we'll see this worked out for 1D, but we can work that. Okay, so I'm actually going to use my blue later, so I'll leave it open for now. Okay. So J is called a coupling constant, and it determines the strength of neighbor-neighbor interactions. Okay, so J is the coupling constant. And it determines strength of interactions. And that's pretty obvious. Determines strength of interactions. Okay. So this is really the only model we're going to work with. This you can do in your homework, and then we're just going to go to this model. We're going to do this model with and without an external field. Okay, so we are going to, we will analyze this model both with and without external field H. Okay. So, when we do it analytically, we're not going to have the field. When you do your computer simulation project, you will put the field back in and see what happens. Okay. So let me tell you, we're going to do this model. We're going to do one dimension first. But before we do it, let me tell you what we're looking for, because it's good to know what we're looking for before we solve it. And so what we're looking for, when J is positive, we're gonna consider positive values of J. J could be, it's positive for a ferromagnet, it's negative for an antiferromagnet. We're gonna consider positive values. When J is positive, it's favorable for spins to align, right? Because if they align, then this times this is positive, and I get a negative, so my energy goes down. And that's a favorable thing for my energy to decrease, right? That's why crystals are more favorable than liquids. So when J is greater than 0, okay, it is energetically favorable for spins to align. Okay. So it's pretty intuitive that if I apply an external field and my field is strong enough, I could make all the spins go in the same direction if I wanted to, right? I could just apply a strong enough field. I don't care about anything. I know I can apply a strong enough field for all the spins to go in the same direction. A more interesting question is, what if there's no field? If there's no field, could this interaction between spins by itself drive spontaneous magnetization? Right? If I just have a material like iron, a magnet, and I don't have a field, could this interaction between spins drive the thing to spontaneously magnetize? Right? So that's a more interesting question. So the question is, okay, can this model predict spontaneous magnetization? Presumably I need to be at low temperature, right? Because, well, if the system's aligned, we have high or low entropy. What do you think? Low entropy, right? So the entropy is going to be greater if the system's disordered, right? So entropy doesn't want it to be aligned. Energy wants it to be aligned. And so we go to low temperatures to favor energy over entropy, right? So question, can we have spontaneous magnetization in absence of external field? In absence of external field. Okay? And what if we can, okay, probably this is going to be at low temperature where energy wins over entropy, right? So E, let's just say E beats S. Okay, right? Energy beats entropy at low temperature. Okay? We don't know. We'll see if this can happen. In principle, based on physical experience, we think it can happen because we know iron can form a magnet, right? So let's define the magnetization. Okay, so the total magnetization of the system is I told you that the magnetization per spin is little mi. So the total magnetization is just adding up the magnets for every spin. So I just have to sum over little mi, right, to get the total magnetization. Let's write it as an ensemble average. So that ensemble average of capital M is the average of the total magnetization. And like I said, I just have to sum over the magnetization of all my spins, mi. If I plug in for mi, I just get sum over I mu si. Okay? So this is the equation you're going to use in your computer code, right? When you do a Monte Carlo simulation, this is the equation you're going to use to calculate the average magnetization of the system. So this is how you're going to compute it in your computer code. You will analyze your Monte Carlo simulation. Okay? Right? You'll just, on your computer, you'll have your system of spins. You can add up all the magnetic moments of each spin, and you can average. And that's how you do it in a computer simulation. Okay, so here's what we're looking for. If the system has spontaneous magnetization, then what we'll see is a diagram which looks like this. Okay? If we plot temperature on the x-axis, so here's temperature, okay, and we plot average M on the y-axis, the magnetization versus temperature. If this is impossible, if my system can't have spontaneous magnetization, I would just get 0. Right? Here's 0 magnetization. This is 0. And so I just get a flat line. And it turns out that's what I have at high temperature, right? So at high temperature, I have a flat line. I'm on 0. Okay? So I'm at 0 at high temperature. But it turns out something happens as I drop the temperature. I start to have spontaneous magnetization. What do you think I should call the point where I get off 0 and I start having magnetization? You want to have a guess?
The critical point.
Critical point. That's a good. Let's call it the critical point. Right? So let's call this the critical point, TC. Okay? And something special happens at TC where magnetization starts to grow. Okay? And is there a upper bound for my magnetization? Sure there is. The most it can be is n times, if they're all aligned, right, it can be n times mi when they're all aligned. It can, actually, the upper bound is n times mu. Right, if all the SI are 1, they're all aligned, so the upper bound is n times mu. And so my upper bound is n mu is my upper bound. So I know it can't be higher than that. This is all spins aligned, right? And so in my critical point, something starts to happen and it starts to climb. Okay? And it starts to approach this value. Okay? And so this is spontaneous magnetization. We call this ferromagnetism. Okay, so this is ferromagnetism. Essentially, it's spontaneous magnetization. Okay? And so, I'm telling you this is true. We can rationalize it based on what we know about magnets. And so our goal is to derive this. Okay? Our goal is to derive that this phenomenon exists, that there exists a temperature, a critical temperature, above which you don't have magnetization, below which you do, and to predict what this curve looks like. Right? So our goal is to predict this curve. This behavior. Okay? That's our central goal of the Ising model. And if we're able to do that, that's pretty cool, because we're able to prove the existence of a ferromagnet, and we're also able to find a system which has a phase transition. If you use your imagination, I told you that it's really important to use your imagination when you do an Ising model. Right? Because the Ising model can map onto many different physical problems. If you use your imagination, does this kind of look like a diagram we drew last time when we were talking about phase diagrams? Can you what phase diagram did we draw last time?
Water.
Yeah, and what were the axes we drew?
Density.
Density versus temperature. And what did that look like? Without worrying about the details, I saw this. Okay, what if you flip this on its side? Does it look like half of the row T phase diagram? Yeah, it does, right? So to realize this kind of looks, okay, note this diagram looks like, it looks like our liquid gas phase diagram, where we have rho T, and we have this, right? If we ignore the asymmetry, right, and here's my gas, here's my liquid, here's my critical point, right? If I just worry about half of this and I flip it on the side, it kind of looks like this, okay? And the reason is that rho, you can map rho to this magnetization. You call rho the order parameter for the liquid gas. Okay, it's just a parameter that distinguishes between the phases, and the magnetization distinguishes between whether you have a ordered magnet or a random system. I'll talk about that more later, right? But just realize these look the same. For now, that's the only point. These look the same. So this tells me something more fundamental about general processes because of this. You call this the isomorphism. Okay, so that's our goal. We want to predict this diagram. Let's go to the 1D Ising model and see if we can do it. Okay? So I want to start on a fresh board over here because this gets a little technical. Okay? It's a little complicated proof, but bear with me because it's cool to be able to derive a closed form solution. And Chandler doesn't go through it. Right? Chandler just gives you the result and says, figure it out yourself. So we're going to go through it. So, okay. 1D Ising model. Well, yeah, okay. 1D Ising model. 1D Ising model. So, without a field. So we have this energy function. We need to discuss how we're going to do this double sum in one dimension. We're going to drop this, and we're going to try to solve for the partition function. Okay? So this is going to be no field. So let's draw our system first. We'll talk about the energy function. We'll talk about how we're going to solve the partition function. So this gets back to John's question. What do we do about the boundary? Okay. You can think we have a line of spins, and so every spin is the same except till when we get the edge. And then the edge is weird. So what we're going to do is we're not going to allow an edge. We're going to consider a ring. Okay? So we're going to put all our spins on the ring. Draw a ring, and it's going to be essentially an infinite ring. Right? So I'm drawing it really long in this direction because it's basically a line of spins and then it bends back on itself so that it doesn't have an edge. Right? So you're going to put your spins on the ring. Here's where the first spin starts. So this is spin 1, this is spin 2, this is spin 3, this is spin 4. You go all the way around the ring, all the way around, all the way around, all the way around. And then when you get to that, when you loop back on yourself, this is spin n over here. This is spin n minus 1. This is spin n minus 2, etc. Okay? And so we use a boundary condition. Okay? So we're going to use what's called periodic boundary conditions. And the reason we do this is that so that all spins are treated equally. We need symmetry. If we don't have symmetry, we can't solve the problem. So the periodic boundary conditions is the spin of n plus 1 is just s1. Right? We go around the ring, we go all the way to an n, and when we go one more, we're back to 1. Right? So Sn plus 1 equals 1 is the periodic boundary condition. And so the question is, are we allowed to use a ring? Is a ring going to give us a different result than a line? What do you think?
Not really. It's a big enough ring, it's basically a line, right?
Exactly, right? So if we had a small system, if we only had 5 spins, then yes, a ring and a line are different, right? In the thermodynamic limit as n goes to Avogadro's number, or infinity, then we're only distinguishing 1 out of the 10 to the 23rd interactions. How can one interaction influence a system of 10 to the 23rd particles? It can't, right? So the point is that for a large enough system, right? And in your computer simulation, you're going to answer the question, what is a large enough system? And you'll find that you converge pretty fast. By the time you get to like a 50 by 50, for sure 100 by 100 lattice, you don't see any difference. So for a large enough system, really, as n goes to 10 to the 23rd, there's no distinction between a line and a ring. It is no difference between spins on a line and spins on a ring. Okay, so we're going to use the ring. Okay, so this is our system. Now we're going to drop this term, and so my energy function is just this. So the energy is, I'm going to call it an energy function instead of a Hamiltonian, because I don't want, well, one, we're not really doing quantum mechanics, and two, I don't want to confuse the H's with each other. So the energy function is, E is still a function of the set of spins, okay? We drop this term, so it's just the interaction, so it's just minus J sum over Ij prime Si Sj. Okay. Just this. What we're gonna, so think about what I told you about this double sum, and think how it applies to this system. Now I only have one dimension, right? So my interactions are, where's my blue marker? My interactions are, 1 interacts with 2, that's one term in this. 2 interacts with 3, 3 interacts with 4, all the way, it's like, the interactions are like links on a chain, right? And then you interact here, you interact here, interact here, okay? So it's like chain links are all my interactions. Is there any way I can rewrite this so I can drop the J? Yeah, exactly, right? So the nice thing about 1D, and the reason you can solve 1D, is that your double sum, your restricted double sum, actually drops to a single sum. Because like you guys said, you can rewrite this. If you think about the links, all I have to do is start sum over I and sum the link for each I. And the link for each I is Si times Si plus 1, right? So this is minus J. We can drop the double restricted sum and replace it by just a simple sum from I equals 1 to n, Si plus 1. Okay? So that's a nice trick that helps us solve the problem. Everyone see that? Okay. So, this is our energy function. I can erase all this now because all we have to do is deal with this. Let's write down our partition function. Okay, so our partition function is, right? Let's solve the partition function. Okay? And so if the first step is to write your naive expression partition function. Right? So we write our naive expression. Q is the sum over states of the system, e to the minus beta e nu. And of course your job is to realize what the states of the system are and plug those in. Okay? And so this is our naive starting point. Naive starting point. it's naive because we haven't really specified what the nu are, right? Nu is just an abstract notation for a state, but we've already said what the states are. The state of the system is specified by the set of all the spins SI. So what nu really is it's a particular set of SI. And we know that the energy depends on the set of SI. So we can plug in the set for nu. So Q, instead of summing over an arbitrary parameter nu, we have to sum over all possible sets of spins. So this is just shorthand notation for saying that we have to sum over all these sets of spins. Now we can plug in what our energy is. In terms of the spins, we have minus beta, and our energy is, we have a minus beta and a minus j, right? So let me just get rid of those minus signs. The minus signs cancel, we have beta j, and we have a sum over I equals 1 to n, si plus 1. Okay, everyone agree with that? Really, really important when you're doing problems like this. And you always have this kind of form when you have a system, when you have a partition function. You have a sum over states, and generally in your energy function, you have a sum over particles. Okay, these sums are very different things, right? So this is a sum over spin states. Right? And this is a sum over the actual spins. Right? They're very different things over particular spins. Right? Very different types of sums. Everyone agree with me? Yeah, okay. So, how do I sum over the different spin states, right? Essentially, so what is this, right? Well, these are just the vectors, right? You could say these are all possible. They're all possible, essentially vectors, right? Where you define the spin of S1, so you would have 1, minus 1, 1, 1, minus 1, dot dot dot, right? Where this would be the value of S1, this would be the value of S2, right? That's what I mean by this. And then you have any possible vector. Right? And so basically what the sum means is I need to sum over all of these possible vectors. How do I do that? Well, each element can be either 1 or negative 1, and I can choose each element independent of every other element. So all I have to do is I have to sum over possible values of each element of the vector. Yeah? Okay, so I'm going to erase this just so my work is contiguous. And so the really important part of this problem is to realize that this sum becomes this sum over states. I can just replace it as a sum over S1 equals plus or minus 1, a sum over S2 equals plus or minus 1, sum over S3 equals plus or minus 1, dot dot dot, sum over Sn equals plus or minus 1. Okay? That's what this is shorthand for. This is how I sum over all possible spin state vectors. Everyone see that? So that's an important transformation. Yeah? Everyone with me?
So that sum goes from S equals whatever to what? It's just over just two values?
Just over two values. So that's an important point, right? It's you're tempted to write an n here. It's not an n because you're not summing over all spins. The n is in this sum. Right? This is sum of I equals 1 to n. This is sum over all states of my system. And the states of the system are all possible values of spins having plus or minus 1. So there's only 2 terms in each sum, right? So that's a good point, right? Each sum has 2 terms. Right? As I equals plus or minus 1. And so that means there's 2 to the n total terms when I put together n sums, right? Okay, so that's what this sum becomes, and I just bring this down. Okay, so our job is to evaluate this. Doesn't look trivial to me. Chandler thinks it's trivial, I guess, I don't know. Right, this looks kind of hard. We need to do this sum, and then we need to do all these sums. And it turns out we can do this. And we need a nice closed form expression, but it's tricky. So we can go through the trick. Okay, so we need to get a closed form expression for these sums. Closed form expression. So how are we going to do this? And like I said, this is just a trick that is not necessarily obvious from the start. You really have to think about it. So the first thing we're going to do is we're going to forget about all these sums for now, and we're going to think about what this exponent looks like. Okay, so let's focus on this. Okay, and so realize that if we're just going to focus on this exponent for now, we can rewrite this exponent e to the beta j sum over I equals 1 to n si plus 1, right? This is an exponential. The sum is a product of exponentials, right? Everyone agree with that? So I could write this as a product notation from I equals 1 to n, the product of these exponentials, e to the beta j si plus 1. Okay? So that's my first step. My second step, let me go over here. I think I can do it in this space. I've written this as this. Now I'm just going to, so I picked this out, I'm going to focus on this. Now I'm just going to pick out this exponential from the product, and I'm going to rewrite that. So I'm going to rewrite this using hyperbolic sines and cosines. That's why I discussed the hyperbolic sines and cosines. So let's look at this. E to the beta j si plus 1. What values can si times si plus 1 have if they're both either plus or minus 1? Plus or minus 1, right? So this thing is either plus or minus 1. So this thing it's one of two things. It's either e to the beta j if the product is 1. Right? If the product is 1, it's e to the beta j, or it's either e to the minus beta j if the product is minus 1. Okay? And so I can use this trick, and let me write it down and then I'll explain it. And so it turns out we can write this exponential, e to the beta j si plus 1, in terms of hyperbolic sines and cosines like this. We can write hyperbolic cosine beta j plus si plus 1 hyperbolic sine beta j. Right? And so this is an exact identity. Why? Well, I shouldn't have erased it. But the hyperbolic cosine of beta j is e to the beta j plus e to the minus beta j over 2. Okay? Let me just put it up here so I can explain it. This is another aside, right? My hyperbolic cosine of x is e to the x plus e to the minus x over 2. My hyperbolic sine is e to the x minus e to the minus x over 2. Okay, so see what happens here. If this thing is 1, then this needs to be e to the minus e to the beta j, right? To get e to the beta j, I need to take this plus this, right? Because if I add these, then these two add, these two cancel, and a factor of 2 times 1/2, so I get e to the x, right? So if I add these, I get e to the x. Everyone agree? If si times si plus 1 is 1, then I'm just adding them. And so I add them, if this is true, and I get e to the x. If si times si plus 1 is minus 1, then I'm subtracting the hyperbolic sign. So I'm taking this minus this one disappears, and I get e to the minus x over 2 minus a minus e to the minus x over 2, so I get e to the minus x over 2, which is this. Yeah? Everyone see that? Okay, a little tricky, but this is an identity because of adding and subtracting those in the right way. Okay. It gets a little trickier, I hate to say it, but let's keep going. Okay, so now what I've done is I can rewrite my partition function using these. I can take this equation, I can substitute this equality, and I can substitute this combination of hyperbolic cosine and sine in for my exponent. And when I do that, I get this. Okay, so after these manipulations, I get Q is the sum over spin, sum over S1 equals plus or minus 1, sum over S2 equals plus or minus 1, dot dot dot, sum over Sn equals plus or minus 1. This becomes a product. Product I equals 1 to n. Then I substitute this in for here. Hyperbolic cosine beta j plus si plus 1 hyperbolic sine beta j. Okay, and let me erase all this stuff so I have room. Everyone see that? Yeah? Okay, now for the trickiest part of the problem. What we're going to do is we're going to focus on what the products of these terms look like. Okay, so imagine I had basically, this is kind of like x plus y to the n, right? I'm taking a product of something n times. So when I take a product of something, if I had x plus y to the n, I would get x to the n plus x to the n minus 1 y plus x to the n minus 2 y squared with some coefficients, right? And that's what this is going to look like. It's going to look like hyperbolic cosine to the n plus a hyperbolic cosine to the n minus 1 times a hyperbolic sine, right? Times a hyperbolic cosine to the n minus 2 times a hyperbolic sine. So let me write this down. So consider the expansion of the product. Of the product. Okay? So the expansion of the product gives a sum of terms, just like x plus y to the n gives a sum of terms. It gives a sum of terms which look like this, of the form. They look like this. They look like a hyperbolic cosine beta j to the n minus a, right? For all values of a, right? Just like we could have x to the n minus 1, x to the n minus 2, times a hyperbolic sine to the a, right? So when I add these powers, I get n, just like when you expand to x plus y to the n. You have to get n when you add the powers. But my hyperbolic signs bring along these spins, right? There's always a factor of an si times a si plus 1 carried with a hyperbolic sign. We don't know what they are, but we know that the hyperbolic sign is going to bring down some spins. So we're going to have some spins with it. Si plus 1, dot, 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 Sj plus 1. Okay, everyone see that? They're going to look like that form. And we're going to have a bunch of different sums of terms like look like this when I expand this product. Okay? Everyone with me? So what I'm going to do now is I'm going to display this term as a diagram. Okay? So we're gonna write this term as a diagram. So write each of these terms as a diagram. Okay? And so how are we going to do this? Well, we have n spins, so you're going to draw a bunch of nodes on your graph. So draw a bunch of nodes. So we're going to draw a diagram for each of these terms. Okay, so draw nodes on the ring. Each of these is your different spin. Okay, so these are the spins. Okay, and I'm going to use a colored marker. In my notes, I just have bold lines and non-bold lines. So if you don't have a colored marker, you can do what I do in my notes. I have bold lines and non-bold lines. And so what you're going to do is this. You're going to look in this term, okay, and you're going to look at your node, and you're going to say, is this spin in my product, right? So if this is spin 1, I look at my product and I say, is this spin over here? If the spin's over here, then I have a hyperbolic sine term for that spin. If my spin isn't over here, then I have a hyperbolic cosine for that spin. Where I have a hyperbolic sine, I'm going to use blue or bold. Where I have a cosine, I use black. Right? So suppose this is spin 1. Okay, so I'm going to use a black line. This black line is going to be a hyperbolic cosine term. Okay? And a blue line is going to be a hyperbolic sine term. Okay, so use bold lines or dashed lines if you don't have colors, right? So you're going to start at every spin. This is spin 1. Is spin 1 in this product of spins? Yes or no? If it is, suppose spin 1 is in this product of spin, then I draw a line between spin 1 and spin 2. Okay? Because if spin 1 is here, then spin 2 is here because I have Si times Si plus 1. So then I go to spin 2 and I say, is there a spin 2, a spin 3 in this product? If there is, I put another blue line. Okay? Then I go to spin 3. I say, is there a spin 3 times spin 4 in this product? No, there's not. So it's a hyperbolic cosine term, so I put a black line. Right? Black line. And maybe this one has a black line. Right? And then maybe that's blue, and maybe this is black. Maybe it looks like this. Okay? So that's how you draw this diagram from this product. And the key point here, right, is to construct this product, all I have to do is I have to go through my diagram. Where there's a blue line, I write down a hyperbolic sine times spin 1 times spin 2. Then I go to the next line. If it's blue, I write down a hyperbolic sine times spin 2 times spin 3. Then I go to the next line, it's black, so I write down a hyperbolic cosine. I go to the next line, it's black, I write down a hyperbolic cosine. And I multiply all those together. And I have n lines, I have n terms. So multiplying n lines together gives me the term, right? So multiplying the n lines together gives each term. Term, I mean this. Okay, this is
Each term in our expansion.
each term in the each of these terms.
Okay.
Each of these terms. So, right, so the black line, I mean, that's just labeled, right? So this could be spin 1, spin 2, spin 3, spin 4, spin 5, spin 6, 7, dot, dot, dot. Right, so this black line would give me a hyperbolic cosine of beta j. This blue line would give me a hyperbolic sine beta j times S2 times S3, right? Times S2, S3, right? This blue line here would give me a hyperbolic sine of beta j times S1 times S2. Right, so that's my rule. Right? You go, if you have a blue line, you multiply by hyperbolic sine and the two spins that the blue line connects. Then you go to your next blue line, you use the rule. If you get a black line, you multiply by hyperbolic cosine beta j. And once you've gone around the ring, you get a term like that. Yeah? Everyone's kind of see that? A little bit, kind of.
Wait, sorry, I'm a little confused about how you know when you get cosine and sine for the terms. Like you're saying if you have S1 and S2 in that product,
So here's the way to think about it. I'm going to give you a diagram. You're not going to draw the diagram. I'm telling you your diagram looks like this. For now, all I want you to be able to do is reconstruct this term from the diagram by just following the rule. By just using the rule that how you construct this term is you go through all your lines in the diagram. Whenever you see a blue line, you multiply by this. Whenever you see a black line, you multiply by this. So the only point right now is if I give you a diagram like this, looks like this, you can reconstruct this using these rules. Yeah? I mean, do you see how if I use these rules, I'm going to get an end product of some combination of hyperbolic cosines and sines
yeah,
with these spins attached?
yeah, I'm just not sure how we constructed the diagram, but that's okay.
So the point is you need to construct all possible diagrams now, right? Because in the product, this product is going to give you all possible diagrams. So what this product is, it's the collection of all possible diagrams you can draw. Okay, so the product, this product here, this product, okay, this product is what it is the collection of all possible diagrams. Right? So that's why the diagrams are nice, because they explicitly tell you how to evaluate the product. Right? How you evaluate this product is you just draw all possible ends. You just draw a diagram, you put all possible blue lines, all possible black lines. And then, once you have a diagram, you use this algorithm to construct the terms. Right? So you draw all possible diagrams, then you use your one-to-one mapping between the diagrams and the terms, and that's how you get the product. That makes sense? Kind of? So you draw all possible diagrams, you map it to these terms, and that's your product. Okay? So that's the most tricky part of this derivation, is to realize how these diagrams map to this, and then the product is actually all possible diagrams. Okay. I know it's tricky. Now we're going to do one more trick and we're going to be done. Now we're going to do our magic trick, and we're going to throw most of them away. Okay, we're just gonna perform magic and say, okay, they all disappear. And we're gonna wave our hands, all but 2 of them are gonna disappear. That's why I wanted the diagrams. Okay, so now what we need to do, to evaluate Q, what we do is we apply these sums to the product, right? I just told you that the product is all possible diagrams. To evaluate Q, what we need to do is apply these sums to all possible diagrams. Okay? To evaluate Q, okay, we apply the sums, sum over S1 equals plus or minus 1, sum over S2 equals plus or minus 1, all of them equals plus or minus 1. We apply all these sums to all the diagrams. Okay. Everyone believe me, right? Because if the product is all possible diagrams, then I'm applying the sum to the product, which is applying the sum to all possible diagrams. So we need to write down each possible diagram. We need to do all these sums for each diagram. Then we add together what we get for every diagram, and that gives me Q. And the good news is they all vanish except for 2. Okay? So everyone believe this? Yeah? Okay, so now what we're going to do is think what happens when we apply these sums to the diagrams. Okay? So what happens? Think about one diagram. What happens when we apply sums to the diagrams, to each diagram? What happens? Well, let's think about it. Anytime I have a blue line, I'm putting one spin product into my term, right? This blue line put a S1, S2 into the product. This blue line puts an S2, S3 into the product. If I have a black line here, I don't have a S3 times S4, right? So consider this diagram. How many times do I see S3 in this term? Once, right? I only get an S3 from this blue line, but I don't get an S3 because I have a black line here. So that's the first thing you realize. If there is any site, I don't care what it is any site where a black line hits a blue line, and blue lines meet, the spin occurs only once. Okay, that spin, right? Each site is associated with associated with spin. So that spin occurs only once in the term. Okay. Why does that matter? So I take this term, S3 occurs only once. I have to apply the sums to this diagram. One of these sums is going to be S3 equals plus or minus 1. The sum that has S3 equals plus or minus 1 is going to have a positive times a negative, and it's going to cancel to 0. So the whole thing is going to cancel to 0 for my sum over S3, because I only have one S3 in the product, and so it's going to give me a positive times the equal and opposite negative. All right? And so the sum of the two values of this spin being plus or minus 1 completely cancel the term. Okay? Makes the term 0. Everyone see that? Kind of? Right? I can write this term as S3 times a bunch of stuff. I don't really even care what the rest of it is. Right? And then I apply the sum over S3, right? You're going to have basically, your term's going to be S3 times a bunch of stuff. Okay? And then when you sum over S3 when you sum over S3 equals plus or minus 1, you get your bunch of stuff minus your bunch of stuff equals 0. Right? Yes?
So is that Q that's equal to 0?
That's a good question. That is the contribution of this diagram. The
So
contribution of this diagram equals 0.
What is that whole diagram?
Of the whole diagram.
So that's the term in our product.
So Q, right? To evaluate Q, what we have to do is we have to take each diagram and we have to apply all the sums to the diagram and we have to give that contribution to Q.
So the only two contributions that matter are the spins aligned one way or the other.
That's exactly right. Right? So the only two that contribute are if it's all black or it's all blue. Right? So it's tricky, right? But it's worth the effort, because after you've gone through all this effort to rewrite your exponential, to draw your diagram, you realize that your product is all possible diagrams, and Q is the contribution of each diagram after you've applied the sum. Then what you have to do is think about the contribution of each diagram when you apply the sum, and you realize that any diagram where a black line hits a blue line is going to contribute 0 after we apply the sums because of this. Yeah? So I think people are kind of seeing it. It's tricky. You may have to think about it more, but let me just write down what Rebecca said, right? So the only diagrams that contribute to the partition function contribute to Q. Okay, after applying the sums, right? Because we have to apply the sum to the diagram to add it to Q. Right? Are all black lines and all blue lines. Right? Because any diagram where I have a black line hitting a blue line is going to give me 0, right? Any diagram where black, blue lines meet gives 0. Okay, so I'm almost out of time. Let me just write it down, and we can think about it more, and we can talk about it more next time. And so this means that after dropping the zeros, okay, after dropping vanishing diagrams, okay, my Q becomes, I still have to sum, right? I'm just going to put my two diagrams in that don't vanish, but I still have to do my sum. Sum over S1 equals plus or minus 1. Sum over S2 equals plus or minus 1, dot, dot, dot. I still have to sum, and I have to sum my two diagrams that don't vanish. So my two diagrams that don't vanish are all black lines. What is all black lines? What is this term? What is the term for all black lines? This thing to the n, yeah? So all black lines is this. Cosh beta j to the n. Oh, I'm gonna run out of room here. This is all black lines. I mean, you have a big parentheses. So all black lines. Okay, and then I have to add my diagram for all blue lines. All blue lines is hyperbolic sine to the n, and then I have every single spin squared, right? Plus hyperbolic sine beta j to the n times s1 to the squared s2 squared dot 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 sn squared. Okay, I know I'm out of time. Let me just write down one more expression. S1 can be plus or minus 1. When I square it, it's always 1. Right? So all these things squared are just 1. Right? These are just 1, 1, 1. And so let me just write it over here and then I'll be done. Right? So my final expression is that because all those spins are squared, I have Q equals sum over S1 equals plus or minus 1. Sum over S2 equals plus or minus 1, dot, dot, dot. Times hyperbolic cosine beta j to the n plus hyperbolic sine beta j to the n. Okay? And that's where we'll pick up next time. So, tricky lecture. It's always a tricky lecture every year, right? But it's worth going through the transformations because at the end of the day, we get a nice simple expression. And if you realize this expression is going to simplify because there's no spins in here. And so we'll do that next time. So think about this, and we'll talk about this next time. Think about the diagrams, and we can talk about it more if you have questions.
Board.
What's that?
Approval marker.
Oh, thanks. Absent-minded. I'm so absent-minded.
It's a nice marker. I'm assuming.
Yeah, and I have a whole pack of black markers, but that's my last blue one, so I should try to keep it.